Hi everyone. In today's video, we are going to talk about convolutional 1D networks. Till now, we were able to consider the convolution operation for images which are at least 2D in shape. We have a 2D image when it is a black and white. We can have a 3D image when we have an RGB image. However, the concept of convolution to extract feature extends to one-dimensional arrays as well, as shown over here. Ideally, we will have a feature vector on which we will apply a convolution to get an output. We will apply the convolution on the output vector again as well. We can see that we are iterating through two layers to get the output. All these things will become clear once we start explaining with some abstract values. For example, this x is considered as an input feature vector, which is of shape 1 cross n. We have a kernel k, which is having only 3 elements, and this is a kernel of size 1 cross 3. On performing a convolution, we get a value like this. The first value y1 will be k1 into x1 plus k2 into x2 plus k3 into x3. So we take the first 3 elements of x and we perform the dot product with the elements of k. So this is how y1 is calculated. We calculate y2. Over here we consider a stride of 1, which will mean that first we consider x1, we just move a step ahead and start with x2. So y2 will start as usual, like k1 x2, k2 x3 and k3 x4. Like starting from x2, the next 3 elements of the vector x are considered, x2, x3 and x4, and then we do the dot product of k with all the 3 subvector considered. The only thing is, while we are performing a CNN on a 2D matrix, we were able to consider a submatrix. Like in previous videos, we used to find a submatrix of size 3 cross 3 from the given set of matrices. Over here, we don't have a matrix, we just have a vector. So it will be just a subvector. So in order to calculate, let's say for y2, we consider x2, x3 and x4. This is the subvector which I have considered, and then I multiply or do the dot product with k, and then the y2 is calculated over here. The process goes on, and the notation which we used previously will remain consistent over here as well. Like if I am having a stride of size s is equal to 1, I am considering a stride of s only. The input vector is of size n, so it's n, the value of n is n, the value of f is 3. Now the size of the output vector, which is y, it's going to be n minus f by s plus 1, which is nothing but n minus 3 by 1 plus 1, which is n by n minus 2. So it will be a vector with 1 row and n minus 2 columns. So it's like y transpose over here. This is x, which is a row vector. We have a kernel k, and on performing the convolution operation on x, we get a row vector which looks like this. So yeah, this is how we apply a convolution. This is one step of convolution which we have applied till now. We can perform the convolution operation again on y1, and just to give a context, this is how it is going to be looking like. We consider that initially we have x, we get y on performing the kernel convolution k on x. On performing kernel convolution k on y, we get z. Now the first element of z is z1, which will be nothing but I take the first 3 elements of y and multiply it with the kernel values, or we calculate the dot product of the kernel values with the first 3 elements of vector y, which is k1 y1, k2 y2, k3 y3. We just substitute the value of y1 over here, which we calculated. This is the value of y1 we calculated just a step above, and similarly we substitute the value of y2 as well, which we calculated a step above, and similarly we substitute the value of y3. We solve a bit further, and then we come to a conclusion that the value of the vector which is supposed to be at this stage, the third stage, is very much dependent on the value of vector which is at the input stage. So on solving further, I am able to express z1 as the sum of coefficients of some kernel, the kernel is not yet known, with the input parameters. Just to see how many input parameters were needed to calculate Z1, we needed X1, we needed X2 over here, we needed X3 over here, we needed X4 and X5. So practically, if I have to think in this way, that I start from an input vector X, I go to Y and I go to Z, I can straight away jump from X to Z by considering the first 5 values of X, and a kernel could be determined accordingly. So how do we actually determine it? The process will be discussed in a short while. So this is how the flow was, from X to Y, from Y to Z. Now I can straight away jump from X to Z by considering a kernel K, which is going to be K1 square, comma, twice of K1, K2, then K2 square plus twice of K1, K3, comma, twice of K2, K3 and K3 square. So if we look carefully, we were able to jump from step X to Z, or the input feature X to Z, by considering a kernel of size 5. So we just needed to have a 1 cross 5 kernel instead of using a 3 cross 3 kernel twice, right? So 1 cross 3 kernel twice. So we used a 1 cross 3 kernel while moving from X to Y, and we used a 1 cross 3 kernel again from moving from Y to Z. So just imagine the number of operations that went through in getting the final result. We can avoid all this by increasing the increasing the kernel size in order to go from X to Z. This is going to save a lot of computation time, and this is the advantage of using kernels while performing a convolution, that you can actually reduce the number of layers in the learning process by making it learn a bigger kernel rather than making it learn a smaller kernel twice in the same path, both forward and backwards, because that's how a training step is performed. So just to reiterate what we did over here, we spoke about an input vector being of size 1 cross n. We have a kernel of size 1 cross 3 using the same formula which we were using in the last two videos. We were able to get the size of output, which is y. We apply a convolution operation again, and we were able to get the first element of z. We could generalize it to get the nth element of z, and then we realized that to calculate one element of z, you need 5 elements of x, and hence a kernel of size 1 cross 5 will be sufficient to move directly from x to z. By doing so, we would be avoiding an unnecessary step from going from x to y and from y to z. So we now proceed further to solve one of the questions that I was able to find from Chegg, which will help us to understand the concept in a much better way. So over here we have the usual input data x1 to xn. So this is just an 1D data which is given to us. So it's already told that we have to consider a 1 cross 3 convolution, and the kernel is this, which is of size 1 cross 3, and the output is generated by stacking 4 such operations on 1D input data. So let's understand what it means. So there is an input data which is going to generate an output matrix. This is just one such operation which is done. It is going to generate another output matrix which will generate another output matrix, and then finally we will get the final result. Let's say it's like this. Now there are how many? 4 layers of convolution which is happening with just an 1 cross 3 matrix or a vector over here. So what the requirement is, what is the width of the equivalent operator O that will give the same output when applied only once on the input data. So instead of applying the same operation 4 times, they want the operation to be applied just once. It's pretty obvious that the usual size of the kernel is 1 cross 3, as we have seen from just an abstraction above, the way we were explaining. The size of the input kernel, if we have to iterate from x to the final step, is going to be bigger than 1 cross 3 only, but we need to know how much bigger it is going to be. There is actually no formula for that, but a little bit of observation done on 1 or 2 steps will actually give you the result. So let's proceed and try to see what we can do over here. So this is exactly how the ask was. So from X to Y, this is the first layer of convolution. From Y to Z, this is the second layer. From Z to U, the third layer. From U to V, the fourth. What they want is from X to directly V. And we need to design a kernel of a suitable size. And as of now, they didn't ask us the kernel, but they just needed to know that what is the width of the kernel which is supposed to be needed. So let's start from reverse. We can say that if we are at V, and this is actually the idea we should be doing, instead of moving from X to V, which can make the things a bit messy, always move from right to left. We start from V and we go to U. So we see that if one element of V1 is considered, like V could be of the form V1, V2, and so on. We don't know the extent to which it will go. But as of now, just we consider one element of V1, and let's see how many X's are required to generate one element of V1. But for that, the first thing we need to understand is how many U's are needed to generate the first element of V1. So V1 could be represented as this K1 U1 plus K2 U2 plus K3 U3. So definitely there is going to be a vector u over here. U will be of this form, u1, u2, u3, and so on. We don't know the extent to which it will go, and we don't even care as of now. But what we care is the fact that the first three elements of u needs to be in a dot product with the vector k, which is the kernel which they have given over here. So v1 is k1 u1, k2 u2, k3 u3. We go with that. Now we try to see how many units are needed to generate this u1, u2, and u3 from Z, because this is the bare minimum requirement. Like in V we have v1. For v1 we need at least u1, u2, and u3. Now from u1, u2, u3, this is the fixed requirement as of now for generating v1. Now for generating u1, u2, and u3, we need to know how many z's are involved. So we proceed further and then see that u1 could be written in this way: k1 z1 plus k2 z2 plus k3 z3. Obviously z is going to be something like this. This is z1, this is z2, this is z3, this is z4, and z5, and so on. This, where it will go we don't care, just we consider the first few elements. So the u1, the first three vectors are taken from z vector, and they are dot product with k, and this is exactly what we get. For u2 we take z2, z3, and z4 dot product with k, we get this as u2. And for u3, z3, z4, and z5, we take these three elements, do the dot product with k, and then get u1, u2, and u3. Now let's try to understand how deep the problem has propagated. So for calculating v1, we need u1, u2, and u3. In other words, for calculating v1, we need values from z1 to z5. Now we need to understand, for calculating even the z1 to z5, how many y's are needed in the first place. So I expand it to the requirement we have. Like, we assume that the vector y is going to be y1, y2, and so on. Maybe it is y7, y8, and so on. It goes on. Let me put y3, y4 here as well. So we know that for calculating z1, I consider the first three elements y3, y1, y2, y3, do the dot product with kernel k. This is what we get as z1. For calculating z2, y2, y3, y4, we consider do the dot product with kernel k, we get z2. Then y3, y4, y5 I put as a dot product with k to get z3, and y4, y5, and y6 as a dot product with k for z4, and eventually for z5 we need y5, y6, and y7. So at least the first 7 values of y are needed to get the output z1. So let's understand again what exactly has happened till now. We were supposed to know how many units of X are needed to generate V. We started with V1. We realized 3 units of U1 UIs are needed, U1, U2, U3. And in order to generate the 3 units, we moved a step back and saw that the 5 units of Z are needed to calculate U1, U2, and U3, and hence 5 units of Z to calculate 1 unit of V1. We propagate a bit further, we come to Y and try to see how many units of Y are needed. So over here we realize that we need at least, yeah, over here 7 units of Y to calculate 1 unit of V1. So let's try to see what has happened till now. We are at this stage, and then we see that we need 7 Y1 to calculate 1 V1. Now we are at the final leg where we try to see how all these yi's are generated. So we have an input vector x, which is of the form x1, x2, x3, and so on. We calculate y1 because we know definitely y7 will be needed from y1 till y7. We apply convolution on each of the individual elements. Applying convolution on the first 3 elements will be giving me y1. Applying convolution on the next 3 elements, x2, x3, and x4, will be giving me y2, and so on. On doing so, we observe that from x1 till x9, like from x1 till x9, we're needed to calculate y1 till y7. In short, if I have to calculate 1 unit of v, or if I have to calculate v1, I need 3 units of u1, which in turn will need 5 units of z1, 5 units of z, which in turn will need 7 units of y, and which in turn will need 9 units of x. So if I have to jump straight away from x to v, we definitely will be needing 9 units x1 till x9. So hence we will need an operator of width 9 that will be applied to x to give a v where k vector should be of 1 cross 9. So as per the requirement of the question, which was like, what is the width of equivalent operator O that will give the same output when applied only once on the input data? Now, if I have an operator of size 1 cross n, we can jump straight from x to v without even considering the intermediate layers y, z, and u. So now let's try to solve a similar problem over here, and this is taken from script. The links of the problems I will share in the description. I highly encourage you to go and check and also try out different sort of questions which are there on these sites. So over here we have the same kernel -1 to -1 which was there previously, and we have an input data x which I have mentioned over here, and over here two such operators are being used, which will mean that from x to y this is one operation, from y to z this is another operation. So two such operators are used on this data from x to y, y to z. Now the requirement is from x to directly move to z using just one new operator, which is definitely going to be a bigger size. It won't be like 1 cross 3, it will be more than 1 cross 3. Maybe it could be, as they have mentioned over here, they have already calculated all these things, it is kind of 1 cross 5 only, but we will do it the question from our end to see how exactly the width of 5 is attained and how exactly this kernel is attained. So we proceed and we see that this is the input data which we have considered, and this is the kernel, and this is the path from x to y, y to z. And as usual, we start from right to left. We take one value from z and see how many values of y are needed to generate it. We took z1, which belongs to z, and for that I am able to see that I need y1, y2, and y3. So basically I have a vector y with y1, y2, and y3, and so on. But for generating just one value, I need to take these 3 elements, do a dot product with k, and then we are able to get z1. Now let's see how many values of x's are needed to generate y. So we move from z to y, now we have to move from y to x. So y1, y2, and y3 are necessarily needed. So we need to try to find out how many x's are needed to generate these. For y1, we need to take x1, x2, and x3. So the x is of this form as I have pointed out. We take the first three elements, do a dot product with k, and the resultant is y1. Again, x2, x3 and x4 we do the dot product with k, we get y2. And likewise for y3, x3, x4 and x5 are taken. So overall, we need to take 5 elements x1 to x5 to make a convolution from x to z in one step. This is exactly what we have got, and this is exactly what is written over here, that the width of operator should be 5, right? And the height should be definitely 1 because we are on the 1D space. So over here we were able to solve a part of it. Let's try to figure out the rest of it, how it is going to look like. So that's pretty simple. First of all, so if I consider just z1 over here, so z1 was equal to k1 y1 plus k2 y2 plus k3 y3. So I substitute the values of y1, y2, y3 with the ones involving x1, x2, x3, x4 and x5 in the next step. So we can say that z1 could be represented as this. This is exactly how it is going to look like. So I substituted y1 over here, I substituted y2 over here, I substituted y3 over here, and on solving further, this is exactly what we are getting. And even on solving further, this is the final step which we have got. Now we have this xi's x1 to x5, and we need to multiply it with a kernel of size 5 which looks like this. So we are just going to put the values. We know that k was equivalent to -1, 2 and -1, I guess. Let me check. Yeah, -1, 2 and -1. In the question they use the notation O, but just to make things consistent, I am using the notation k. I just substitute the values, minus k1 square twice of -1 into 2, and on doing so, this is the required kernel which will take into account an input x, and it will convert it into the output z instead of going from x to y and y to z. The size of the kernel was 1 cross 5, and the kernel actually looks like this. So we proceeded with a 1 cross 3 kernel, and then we move to a 1 cross 5 kernel which will do the convolution needed in just one step. On doing so, we were just able to reduce one layer from the network training. So till now, we were trying to solve the problem of reducing the number of layers by using a convolutional 1D, but in real sense, the dimension could be more than that. Just to give an example, we have a kernel over here. This is also an example taken from Chegg only. This is the kernel K, which is -1, -1, 1 and 1, and it is supposed to be applied on a matrix A of which the dimension are unknown, n cross n. So this is a kernel K to be applied on A, and if I just use the formula, it is equivalent to n minus f by s plus 1. This is going to be the output dimension. So on solving it, it is going to be n minus 1. Right. So let's say there is a matrix A. I apply a convolution K to get a matrix B. B will be of order n minus, n minus 1 cross n minus 1, while A was of order n cross n. And if I apply it further to C, then it will be of n minus 1 minus 2 plus 1, which will be n minus 2. So C will be of order n minus 2 cross n minus 2. Yeah. So we have A, we apply the convolution kernel K on A to obtain B. We apply the convolution kernel K on B again to obtain C. And this is the dimensions we are getting after successive application. And over here it said that output is generated by stacking two such operators on 2D input data. So this was A was our 2D input data. This is one such operation, this is second operation, and this is like the final result we are getting. Now we need to find an equivalent operator which will help me in moving from A to C directly without us having to perform the convolution twice. So there is one important thing which is known over here. We can definitely not do the propagation from right to left as we were doing previously. Also, the matrix A is of size n cross n. There could be innumerable numbers which could be there in that value, and we can't generalize it in a better way. So we will start with some point, and if we look carefully, if we select the value of n as equal to 3, so this is what is going to happen. A will be of order 3 cross 3, B will be of order 2 cross 2, and C will be of order 1 cross 1. So iterating from C till A will become a bit easy. So always we need to uh, make assumptions in such a way that the calculations are simplified. So we will just assume a 3 cross 3 generic matrix A and try to move from A to C in the following way. So this is what we did. So we have this kernel K. We write it in a very generic form: K1, K2, K3, and K4. We have a matrix A, which is a 3 cross 3 input matrix. The reason I already explained a bit above, and this is how the abstract form of A is going to look like. We don't assume any values over here. We just assume it is consisting of A1, A2, A3, A4 up to AN. Now, this is how the task was performed. So B will be of size 2 cross 2 as expected. Now we assume B to be another matrix, PQRS. So this is how A was looking like. This is first assumption. This is the second assumption we make on B. And on B, we apply the kernel. So now we know the C is going to have only one value, C1 or just C only. This is going to be attained only when P, Q, R, and S are multiplied with K1, K2, K3, and K4. Basically, the dot product is what is being talked about. So we do the multiplication and we obtain C as this. Now we see over here how P was obtained in the first place. So P was obtained after A1 into K1 plus A2 into K2 plus A4 into K3 plus A5 into K4, right? This is how the element P was obtained. We write it in a generic form, which is like this, and we also substitute the values of K's as well. So the value of K was equal to, let me check, -1, -1, 1 and 1. Okay, -1, -1, 1 and 1. This is the value of A, which is A1, A2, A3. This is A4, A5, A6, A7, A8, and A9. So we have this as the A matrix, and we have the output matrix as PQRS. So P was done using A1 into K1 plus A2 into K2, A4 into K3, and A5 into K4. We just put the values of K's and then we get P as this. Now let's see how Q was generated. It was A2 into K1 plus A3 into K2 plus A5 into K3 plus A6 into K4. We put the values of K1 and K2 as -1. K3 and K4 remain 1 as well. So we get the value of Q as this, and similarly we calculate the value of R, and eventually we calculate the value of S. Now we know that how we were able to reach from PQRS to from PQRS to C. So we knew how we were able to reach from A to B. This is the set of operations needed to reach from A to B. We know the set of operations needed to reach from B to C. This is exactly what we have. Now we just have to substitute the values of PQRS, which I obtained from the first step over here. So this is the value of PQRS, which was there. I do the substitution and I get something like this. So this is, if I look carefully, we can see one A1, there is one A2 over here, A4 is there, A3 is there, A5, A6, A7, A8 and A9. All these values are present over here. Now, if I look into the matrix carefully, like A1, A2, A3, like this is the A matrix which we were having, and also the coefficients which we have got corresponding to the calculations done over here, we can very well see that the kernel should be somewhat like this: 1 2. This is for A1, this is for A2. Write the coefficient of A3 as 1. Look at the coefficient of A4, it is -2. For A5 it is -4. For A6 it is -2. A7 is 1, A8 is 2 and A9 is 1. Right. So we can say that if I consider a matrix like this and I do a dot product with A, I am going to get the value as C. So this is equivalent to saying that if I have to reach from A to C, we have to multiply with a kernel which I write over here. This is the kernel which is needed. So we can say that this is the kernel attained for directly obtaining C from A, and we need to use a 3x3 kernel on a 3x3 matrix to get the result C as needed. So this is how the kernel was supposed to look like. So if we see the question carefully, this is the requirement. Like we started with a 2x2 convolution kernel, and we did two stackings like from A to B and B to C, but we never wanted to apply two operations in the first place. The resolution to that was applying a kernel of a bigger size, which we were able to comfortably obtain by backtracking and making a little bit of substitutions to get the kernel as this. The only requirement is when we were moving in a 2D domain, we can't move from right to left, so we have to make the assumption simple from the first step itself. In the first step only, we assume that we are considering a matrix of size 3x3. So had we considered a matrix of an abstract size n cross n, iterating from there to here will be a bit tough. So we can definitely consider a matrix of size n, but it is always advisable to start simple so that we can at least know how exactly we need to reach. So in a lesser number of steps without much calculation mistakes done. So we start with 3x3. We knew that we will be able to reach 1x1. We do the operation stepwise from left to right. We don't move the usual backward step from right to left. We move from left to right and we obtain the equation of PQRS, which is B, and then we obtain the equation of C as well. We do the substitutions and eventually obtain the kernel, which looks like this. So that's it for today. I will stop over here. In the next video, we will be talking about another important concept called as pooling. Thanks for your time.